Okay, so this chapter we've alluded to many times. I'm trying to get you to understand how chemistry can help you see how the world works. So it's called intermolecular attractions. That's between molecules. In contrast, bonds are intramolecular attractions, and they're way stronger. So here's the approximate strength of a single covalent bond. Here's a double. You can see it's stronger. A triple is even stronger. And ionic bonds can be quite a variety, about the same as a double bond, but they can be quite high. And then intermolecular attractions are not bonds, even though one is called a bond. It's not a bond. Look at the magnitude here. It's just orders of magnitude smaller. Ion to dipole attractions, I really can't find anything that, how do you say, that describes it, so I just put variable. So the premise is that a polar molecule behaves like a little magnet. It's therefore attracted to other little magnets. Whereas a nonpolar molecule, like a piece of aluminum, is not going to act like a magnet. If you take a magnet and put it up to a piece of aluminum, they don't even know each other's there. If you take two magnets, put them up against each other, there's going to be repulsive forces and there's going to be attractive forces. So a polar molecule has to have a dipole in it. So if I have a positive charge here, it's going to be repelled by the partial positive on the polar molecule. It's going to be attracted to the partial negative on the polar molecule. But if it's a nonpolar molecule, there's simply no attraction. So we'll go through all four of them from the weakest to the strongest. So London's forces, and often confused with van der Waals. Van der Waals really means everything. London's forces are the very weakest. They only occur when the molecules actually collide with one another and they're deforming each other's electron clouds. So here's two atoms or molecules. You see I put the electron clouds as being symmetrical. They're nonpolar. When they collide into each other, I drew it so one completely won and the other completely lost, which is not exactly what happens. But notice that the electron cloud here on the winner has pushed the other electron cloud way over here because electron clouds repel one another. So during this collision, by pushing that electron over there, I made a dipole. Here's the partial negative, here's the partial positive because it's so close to the nucleus. But this is a temporary dipole. It's only going to happen during the collision. So a better way to think about this is they collide and these things oscillate back and forth like this. And during that oscillation, they're attracted to each other. So here's a way to think about this. Two particles crash together. For one fraction of a second, they're deforming each other's electron clouds. Then they bounce away just like nothing happened. There's no loss of energy during a collision. Electrons don't actually bang into each other. Electrons don't experience friction because they simply pass through empty space. But during that time of the collision, there is an attractive force. So this is extremely weak. But you know what? If you are a non-polar molecule, this will be the only attractive force you will ever experience. So anyway, just to give you an idea of its magnitude and how important it really is, here's two molecules. So both of them are pentane. So this is called N-pentane, N for normal or linear. This is neopentane, which means it's as branched as you can get it to be. So they have the same molar mass, they have the same composition. The only thing that's different about them is their shape. But the boiling point of this one is 9.5. And the boiling point for this one is 36 point something. How could that be so different? It's because spherical molecules, when they bang into each other, their area of contact, known as their van der Waals contact surface, is small. But linear molecules like this, they can be interacting all along here. So there's more van der Waals contact. The deformation of electrons is more acute. So therefore, the stronger attractive force. And here we're going to demonstrate that in some biological molecules. Fat molecules. Here's a fat molecule. It's linear. All this is carbon, hydrogen, carbon, hydrogen. It's all almost entirely nonpolar. Look at the fat molecules. They're like this. They're right up against each other. And so they're up against each other, and they're not at 0 degrees Kelvin. So they're vibrating. They're vibrating in place. And during that whole vibration period, they're deforming each other's electron clouds, leading to what we call London's attraction. Here's an oil molecule. So notice that these cis double bonds right here are causing these hydrophobic tails, we call them, to go off 120 degrees from each other. In other words, they get kinky. The more double bonds you have in an oil, the more spherical it looks like. And you know what? You can't get those spherical molecules right up against each other because their tails are going everywhere like this. So here's the difference between a fat and an oil. At room temperature, if it's a solid, it's a fat. If it's a liquid, it's an oil. What is the difference? The molecules are the same except for these unsaturated double bonds. So you can see that does make a difference, huh? Well, what if you have two polar molecules? Then you're going to have a dipole to dipole attraction, also known as a dipolar attraction. Keystone is not used very much. So here's a typical small polar molecule. HCl, also known as hydrochloric acid if it's dissolved in water. So the difference in electronegativity is 0.96. So this is a polar covalent bond. These don't have polar covalent bonds. So here's one possibility. The dipole here is repelling each other. Here's the other possibility. This one is switched around and now there's an attractive force. So the strength of the repulsive force should be equal to the strength of the attractive force. However, in nature, one is predominant over the other. So for example, I take a bunch of magnets, I put them in a box, I shake the box all up, I don't have any idea what's going to happen, I throw it across the room and I go, look. What am I going to find with the magnets? Aren't they all going to be clumped together because of attractive forces? They're not all going to be separate because of the repulsive forces. So attractive forces are more dominant over repulsive forces. So yeah, you can take this all the way to love versus hate. Which one is stronger? Love, right? Yeah. Now here's the confusing one. A special strong dipole attraction is often called a hydrogen bond. But these are not bonds, they're simply strong dipole-dipole attractions. To meet that criteria, you need a large partial positive charge on one and a large partial negative charge on the other. Okay, well, how do we get that large partial positive charge? And this is where the hydrogen is involved. We take the three most electronegative elements on the periodic table, F, O, and N, and yes, it does spell fun. So therefore, you will not forget this. Well, it's the Chinese spelling, right? So then we bond them to hydrogen. So hydrogen is 2.20, this is 3.98, 3.44, 3.04. So these are all very polar covalent bonds. But the reason why the hydrogen is important is because unlike any other element, hydrogen has only one electron. And when you start to pull that one electron away, you're partially de-shielding the nucleus. Any other element, if you pull one electron away, there's all the other electrons beneath it that are still shielding the nucleus. So this is why it's known as a hydrogen bond, because the hydrogen supplies the very large partial positive. Then how do we get a large partial negative, in the other molecule? The other molecule simply has to be polar, and it has to contain an F, an O, or an N. So essentially, both molecules have to have some form of fun. Now let's look at a water molecule. So here is a water molecule. I put the partial negative here on that electron cloud. Here's another one. I put the partial positive on that hydrogen atom. Oh, I see that these other, it's good that I can do this in Word. So is this a hydrogen bond? Here's the O of one, right? What does the other one have to supply? Either an FH, an OH, or an NH. And here's the OH. So yes, that's a hydrogen bond. Or you could say, here's the OH in one molecule. What do I need the other molecule to supply? An F, an O, or an N. And here's the O. So again, both molecules have to be polar. So if you look at a non-polar molecule, that's this carbon tetrafluoride. So the carbon-fluorine bond is polar covalent, but yet this is a non-polar molecule because it's symmetrical. My models were closer. So carbon tetrafluoride would be like this, right? It's perfectly symmetrical. So even though these are polar bonds, in other words, they behave like little rockets. If I fire all four of these rockets all at once, it doesn't go anywhere. It's a non-polar molecule. So that would not qualify for this because it's not a polar molecule. So if you took me at my word and you went to the periodic table and you looked to see if F, O, and N were the three most electronegative elements, you would find out that not exactly. Chlorine actually has a higher electronegativity than nitrogen. But why do we not include chlorine in this analogy? If you look at fluorine, fluorine is right there in shell number 2, period number 2. chlorine is in shell number 3. That means that its electrons are in another shell. They're much farther away from the nucleus. And say, for example, you have a negative charge on the chlorine atom compared to the negative charge on the fluorine atom, which is much smaller. What's really important here is not the charge, but the charge density. So this -1 charge divided by this small surface area is quite different and stronger than this large surface area. So electronegativity is very useful for a lot of things, but it's not perfect. It's just a good approximation. So here are some examples of attractive forces and physical properties. Water. So ice, water molecules in ice have about, on average, 4 hydrogen bonds, 4 attractive forces. So here's 1, 2, 3, 4. And what that does is it leaves these voids in here. Remember how we talked about that before? So when you start cooling down water, these things are vibrating more and more slowly around each other. And the more slowly they go, the more effective these attractive forces become, and they eventually line themselves up to maximize the strength of that attractive force, in this case, a hydrogen bond. That leaves this void right there, which causes the volume to go up and therefore the density to go down. So hydrogen bonds are strong enough to break glass. Here's why ice floats on water. Okay. That I put up here. Oh yeah. So another way to think about this, now that you're thinking in terms of intermolecular attractions, when I take ice and I heat it up to melt it, what am I really doing? I'm breaking the attractive forces. Whatever they may be, I'm breaking the attractive forces. Brings us to another example, refrigerants. So here is dichlorofluoromethane. So methane was all 4 of these were hydrogens. They're replaced with 2 chlorines and 1 fluorine. So this is called R22, refrigerant 22. So let's look at it. This bond right here is only 0.35 electronegativity difference. It can only do London's attractions. This one right here can do dipolar attractions. This one right here is capable of hydrogen bonding. Okay. So let's think about this for a minute. How does an air conditioner work? Well, you have a compressor. It's a gas. You compress the gas together, and whenever you compress the gas, the temperature goes up. So you have a fan that blows across this and sends the heat out of the room. Then it comes into the other part of the machine, and the gas is allowed to expand again. So what happens when the gas expands? Well, it gets colder. Take a compressed air tank or something, pop it open, let it come out, and you'll see it gets cold. So then you blow the cold air into the room across that. If you think about what this molecule has to do, if you have only these molecules in here, what is the attractive forces that are possible? There's a dipole to another dipole, right? That's possible. Of course, London's is always possible. But what about hydrogen bonding? Does this molecule have an FH, an OH, or an NH? The answer is no. So it has the potential to do hydrogen bonding, but in the pure state, it does not have that potential. Now, what would happen if some water got in there with the freon? Well, now you would have hydrogen bonding with the water molecules, right? And think about what that gas has to do. It has to be compressible and it has to expand. If you put water molecules in there, you're going to mess around with the attractive forces and all this system is not going to work anymore. So anyway, R22 has been replaced with 134A, and you might wonder why. Here's the ozone depletion potential for both. R22, ozone depletion potential wasn't bad, but at least this is 0. Global warming potential is less, even though the atmospheric lifetime is low. And what does the global warming potential of 1300 mean? That means it's 1300 times more powerful than carbon dioxide. So do we want these things getting loose into our environment? The answer is no. But you, as a human, are you going to let anybody take away your air conditioning? Doubt it. So the last one is ion to dipole attractions. And so why are these the strongest? Because while these are partial charges, one of these is going to be a full charge. So it's going to be a stronger attraction. And if here's the partial positive, I don't have to say exactly which one of these has the partial negative. It doesn't matter. Okay? So you just draw them in the same vicinity. That's all. They're going to be attracted to each other. Jeez. So ion dipole attractions can be used to explain why things like sodium chloride dissolve in water. This is an interesting thought process. The melting point of sodium chloride is 801 degrees. I have to make it that hot before I can cause sodium and chloride to move away from each other. But yet, I can take sodium chloride and put it in the coldest water, and it instantaneously dissolves. Here's the reason why. The sodium gets surrounded by a layer of water molecules. So you see the partial positive being attracted to the full negative. This is an ion to dipole attraction. Look at the chloride. The partial positive of water is now attracted to the negative charge of the chloride ion. So you have a layer of water around here, a layer of water around here. So now look at this positive charge is now spread out over this huge sphere, -1 over this huge sphere. But now this first sphere, called the layer of hydration, has a negative charge, even though it's much weaker than over here. So the negative charge over here is going to attract another layer of water molecules. Same thing over here. So you get these multiple layers of hydration. And what you're really doing is you're making the positive charge and the negative charge so weak that they're not even attracted to each other anymore. So you've broken the ionic bond. So what we're saying really is that the attractions between water and the sodium, between water and the chloride, these attractions are stronger than the attractions between the sodium and the chloride itself. Okay, well, how do we determine if a molecule is polar? This is simply a review from chapter 10. Then how do we draw attractive forces? Well, what we did here, I gave several examples. Draw the strongest attraction between ammonia and hydrogen fluoride. So here's ammonia. I just drew that, okay? Then maybe you could come along and draw this part. So the partial negative is going to be attracted to the partial positive. How do I even know there are partial charges? I have to look at the difference in electronegativity, right? So does this meet the criteria for a hydrogen bond? Here's the FH of one. All I need the other one to have is an N. Yes, that's a hydrogen bond. Here's another one over here. Okay. So what are the attractions between ammonia and hydrogen fluoride? Yes, all of them have Londons. They're both polar, so it's dipole to dipole. Does it meet the criteria of a hydrogen bond? Yes. Is there a full charge? No. So it's not an ion to dipole. So does ammonia dissolve in hydrogen fluoride? The answer is yes, because they're attracted to each other. Here's another one. Here's acetone. Okay, so you guys know what acetone is. It's fingernail polish remover. We sometimes use it to get wax off of surfboards, things like that. And does it dissolve in water? Yes. Does it evaporate quickly? Yes. Why does it dissolve in water? Notice that all these carbon to hydrogen bonds are nonpolar. Carbon to carbon, nonpolar. The only polar bond in acetone is the carbon to hydrogen. Okay, see that over here? So I put charges on it. And then that partial negative is going to attract the partial positive of a water molecule. This partial positive is going to attract the partial negative of a water molecule. So look at this attraction right here. Polar to polar means it's dipolar. Is a hydrogen bond. Well, here's the O. Is that an FH, OH, or NH right here? No, it's not. Here's the O. Here's the OH of the other one. That is a hydrogen bond. So here's between two molecules of acetone. So here's the one polar bond here and the one polar bond here. I align them up to be opposite charges. Here's the O. Do I have an FH, OH, or NH over here? No, I don't. So that's simply a dipolar attraction. So notice that the attractions between acetone molecules themselves are weaker than that between acetone and water. So here's acetone and acetaldehyde. Okay. Now you don't need to know what these molecules are, of course. Here's between acetone and acetic acid. Okay. So just so you get kind of the hang of it, it's always a partial positive that's going to be attracted to a partial negative. That's never going to change. So here's some comparisons. Dipole and a dipole, right? Dipolar. Dipole and a dipole. It's not a hydrogen bond, even though this has an OH right here. There's nothing over here that meets the criteria. Here's an ion to dipole. This right here can do hydrogen bonding, same here. And over here, there's no polar bonds. So dihydrogen sulfide is a gas at room temperature. Water is a liquid at room temperature, even though the gas is twice as heavy. you can see that attractive forces are more important than mass, aren't they? A nonpolar molecule to a polar is only going to be Londons. Here's an ion, here's a dipole. Here's an ion, here's a nonpolar molecule. Guess what? This nonpolar molecule doesn't know whether there's a full charge there, a partial charge, or anything. It doesn't sense it. Simply London's forces. So here we actually drew pictures of this. We drew pictures of this. I actually like to demonstrate this. In labs, I would do this. If I take acetone by itself, I squirt it on the tabletop, it evaporates really quickly. Water, on the other hand, is not going to evaporate very quickly. So I squirt some water and some acetone on the table, then I kind of mix them together with my finger. Will they dissolve in one another? Yes, because of hydrogen bonding. It's going to evaporate more slowly than acetone would, but faster than water alone.
Excuse me, Professor. So because acetone has hydrogen bonds in its atomic structure, and because
acetone does not have hydrogen bonds, only dipolar attractions, which are weaker than hydrogen bonds.
But it does have hydrogen atoms, yes?
Yeah, but this is all nonpolar. So there's no charges right there at all.
Uh-huh.
Right?
Okay. Okay, right.
Okay. Anyway, so here's the OH of one, here's the O of the other one, hydrogen bond. And just to be careful, these are ionic bond. That's an intramolecular attraction. So attractive forces can partially explain solubility, right? So we're talking about over here. Water and oil are not soluble in one another. Air is not soluble in water either. Attractive forces partially explain the physical state of matter, like this table. I know the attractive forces are strong, even if I'm not sure what they are. And the physical state of a substance is determined by at least 4 factors. And I put as number 1, the nature of the substance. That's how important I think it is. And then temperature has to do with it as well because of kinetic theory. So if I increase the temperature, I'm increasing the kinetic energy. 1/2 is just a constant. Mass is a constant. But what's going on is the velocity. I increase the velocity, which means at some point they're going so fast that they can break away from attractive forces. And I also put mass in here because at the same temperature, if I have a large mass, my velocity is going to have to be smaller. So similar type of thing. So here's just a good comparison. Methane is only carbon and hydrogen. It's nonpolar. So methane is a gas because it's small, right? If it's small, weighs not much, you can have a high velocity. Gasoline is a liquid that evaporates quickly. For example, octane. And oil is a liquid that does not readily evaporate. Look how much bigger it is, more than twice the mass. Then tar and bitumen and pitch are solids with very high molecular weight, hydrocarbons, especially called asphalt, especially if we melt it and then embed gravel in it. Let it get hard, so now that becomes a road. And this is how you travel around the place, isn't it? You burn gasoline, you use oil to prevent your engine from getting destroyed, and you drive on the bigger stuff. All coming from fossil fuels. And finally, if you're a gas, pressure is extremely important. You guys know if you take propane gas and you pressurize it, it turns into a liquid, right? Liquid propane. So anyway, I just really liked this one. It was just so stupid. I couldn't help it. And then this one is like, oh, because you're a polar bear. So here are some chemical attractions. Here's some human attractions. And maybe no attractions. So anyway, that's chapter 14. Any questions about that? So then, so chapter 15 sets a logical transformation here. Anyway, here's a little bit of information about atmosphere on planet Earth. Some of you are from planet Earth. Some of you might be just visiting, I don't know. But as you know, water is extremely important, but you have no clue how important it really is. This drop right here, this sphere, represents all the water on planet Earth. Does that surprise you that it's so small? We're known as the water planet. And you see that little dot right there? That's all the fresh water. That's all the water in lakes and streams and everything. And you see that tiny, tiny little dot right there? You might not even be able to see it. That's all the potable water, all the drinking water. So what would happen if the temperature of Earth increases? What happens to water? It evaporates. That's an issue, isn't it? Then carbon dioxide levels have increased by 15% since 1975. It's higher than it's ever been. Methane is another greenhouse gas that people are concerned about. The ozone layer is important. It affects weather patterns. Other things that are kind of interesting, water vapor is broken down into hydrogen and oxygen in the ionosphere. So the Earth is constantly losing hydrogen because water is being converted really into oxygen. Helium also does not get held down by the gravitational field of the Earth. So it's constantly going as well. So global warming is a real threat to our planet. And people who don't realize that, I just don't know what to do with them. I would say that global warming is not going to be a linear increase. It's going to be an exponential increase. And here's two serious problems about it. Carbon dioxide increases. You put it in water, you form carbonic acid. That ionizes to give you the hydrogen ion, which is acidic. So that's going to acidify the planet. One year I was trying to get my chemistry students to get involved in Earth Day. So I took a glass of water to the class and a pH meter and a straw. I put the pH meter in the water, took a deep breath, and I exhaled one time into the water. The pH went from 7 down to 5 something with one breath. No one cared to do anything about it at Earth Day, kind of dissolved, kind of disappointing. And then this acidified environment kills corals. It dissolves calcium carbonate, which is a major structural component of coral. What does it do? It turns it back into what? Oh my God, CO2. It's a problem. So anyway, just a couple of Dilberts on this. I love Dilbert. He's just really too much. So here's one of the major things I want you to get out of chapter 15, and that is to understand the kinetic theory of gases. So kinetic theory is used to explain the behavior of gases. So it's very simple. Gases are small particles. Remember, the noble gases are atoms, the other ones are diatomic molecules. And the kinetic theory says that they're moving randomly in straight line motion. But the word randomly is just because back in the old days, they didn't understand it was just going everywhere. But really, there's nothing random about it. Gases move according to the laws of motion. Simple as that. And the identity of gases is not important in calculations because they're not reacting at the moment. So what they're really referring to is the ideal gas law, PV equals nRT, where N is the number of moles. So if I'm trying to calculate, say, the pressure, I can't do it if the number of moles is changing. I mean, theoretically, you could with calculus, right? But anyway. Gases are mostly empty space. The particle size is negligible. There's independent motion with no attractive forces. So that must be true at the temperature that they exist as a gas, but it might not be true at lower temperatures, right? Right now, our humidity is not 0, so there's water vapor out there. What happens if the temperature goes down? Well, that will all condense into liquid, right? Because of the attractive forces. All collisions are totally elastic. There's no loss of energy during a collision. And here's kinetic theory as it applies to gases. So now, just to give you an idea, and you know what? You just don't see this kind of stuff in a regular textbook. So STP is standard temperature and pressure. So that's defined as 0 degrees Celsius in 1 atmosphere. So 1 atmosphere is the pressure that you're experiencing approximately now at sea level. And 0 degrees is going to be Celsius, not Kelvin, because at Kelvin there is no motion at all. So that's a really, really cold day. So your refrigerator is about 4 degrees, your freezer about minus 20 degrees, right? So anyway, you're down at the beach on a really, really cold day, and at STP, 1 mole of gas, which is that many gas particles, would fill a 22.41 liter container. That's almost 6 gallons. That's the largest gas can you can buy. 6 gallons. So down at the beach at 0 degrees on a cold day, oxygen is going more than 1,000 miles per hour. So to compare that, the speed of sound is less. Bullets from small arms go maybe 2 to 3 times faster than these, but they're booking. In that container, there's about 10 billion collisions per second. So we use kinetic theory to explain the behavior of gases. So why does a gas fill the container, the entire container that it's put into? Because the particles are constantly moving. Why can one gas diffuse through another gas? Because particles are constantly moving, and because gas is mostly empty space. Why are gases so compressible? You can take 80 cubic feet and put it into a dive tank. That's about a 209-to-1 compression. So why can you do that? Because gases are mostly empty space. How does a compressor do that? Well, here's an analogy. Say you have a bunch of people in a room, they all have fly swatters, and there's a bunch of flies in the room. If you simply start all the people from one side and start moving them to the other side, just swatting at these flies, you're going to concentrate the flies in one part of the room. So why does an aerosol can retain its pressure forever if there's no leaks? Because gas particles don't lose any energy during collision. So you can see that it's very common sense explanations. So what I want to do is go through the gas law, P equals nRT, and we'll look at every single entity in that equation and understand them. So the first one is P. Pressure is the force divided by the area. Force is the mass times the acceleration, right? So acceleration is the change in velocity. If I go mass times the acceleration, that's the same thing as weight, right? So pounds per square inch, for example. And so, anyway, it's hard to explain this without being in a classroom to demonstrate some of the things I normally do. But what is 1 atmosphere? Say you're standing right here at sea level. Gravity is pulling this column of air down around you. You are constantly being bombarded from every direction from these gas particles going somewhere around 1,000 miles per hour. So they have mass. They're accelerating off of you when they bounce into you. So they're putting a force on you, and divided by the area of your body, that's a pressure. So this is known as 1 atmosphere. If I go higher up, there's less particles, so less pressure. So some typical units of pressure are given over here. 1 atmosphere is 760 torr, which is a millimeter of mercury. It's about 14.7 psi. Here's Newton per square meters, which is simply a Pascal. You don't need to memorize all those things. So what is a typical passenger car tire? It's about 32 psi, right? Sometimes as low as 28 on certain kinds of cars. So the pressure inside the typical car tire is a little bit more than twice the pressure outside of that car tire. And we use barometers to measure pressure. So here's how you make a barometer. You need a dish and you need a tube. You fill the dish up a little bit with mercury, fill the tube up all the way, and I would put my finger or something over this, flip it upside down in here, and then take my finger away, and this is what I would get. There's a break right here. It doesn't stay at the top. It gets pulled down because of the force of gravity. So this is called the Torricellian vacuum. It's not very strong itself. That's not what's really holding this column of mercury up. If I were to put a hole right here, then this column of mercury would simply go back down here, right? All be the same level. The reason why it doesn't simply drop down is because of unequal pressure. The pressure from the atmosphere is hitting on here, in here, but it's not able to hit on this surface area. It's protected by the glass or the metal, whatever it is. If I put a hole here, then gas particles go in here, and they put the same pressure inside here as they do out here, so the pressure would be the same. So what's in here? It's not air, because I didn't let any air go in. It's a vacuum. There might be some particles of mercury in the vapor, and that is dependent upon temperature. That's why we have to control for temperature sometimes. But the major reason why you get this column right here is because the pressure down here is different than the pressure up here. And liquids tend to transmit pressure. Gases do not. Solids do, obviously, right? But so do liquids. So for example, the brakes in your car, the liquid is really an alcohol. So when you put your foot on the brake, that pressure on that liquid goes through each, through the tubes to each of the wheel wells, wheel cylinders, and puts an even pressure at all of them. Because that's just how liquids behave with pressure. So now, if I'm down at the beach and it's 0 degrees, guess what? I'm going to measure 760 millimeters from this point to that point. 760 millimeters of what? Mercury. And that's the definition of 1 atmosphere. So we use the barometer to decide where there's high pressures in the air, where there's low pressures in the air. And say, here's an example. What if we had a hurricane threatening Hawaii? And then we found out that Hawaii at that point in time was in a low pressure zone. Should we be worried? The answer is yes, because the storm is going to follow where the low pressure is. What if we're in a high pressure zone? And the answer is, you don't have to be that worried, because that will push the storm away, hopefully. So, when you vaporize water, a couple things happen. You heat up water, you put it into the gaseous state. What did you just do? Here you had about 2 hydrogen bonds per water molecule. You get up here, you have none. You simply took magnets and you separated those magnets from one another, but they want to go right back together again. So by vaporizing the water, you created potential energy. So this has everything to do with what goes on Earth, the weather patterns and everything. So sunlight from the sun hits mostly the equator, get a lot of evaporation of water at the equator. Adding a new gas increases the pressure. You're pushing air that way and that way, creating currents, and you're creating currents that take that potential energy different places. So when those water molecules with all their potential energy hit a cold area, what's going to happen? Water molecules are going to condense because of hydrogen bonding. And by the law of conservation of energy, where's all the energy going to go? It's going to use to create havoc. That's where the energy from storms come from. So when the air is humid, we think that, oh, it's hot and all this kind of stuff, but actually the density of air actually decreases with added water vapor. Some objects actually will get heavier because they absorb more water. Yeah, as we'll talk about later, in a humid day, it's hard to get heat energy away from your body because water molecules are constantly landing on your body, which kind of lowers the effectiveness of water molecules leaving your body. So anyway, we have two basic models of pressure. So here's pressure with a variable volume, like a balloon. So in a balloon, the pressure in the balloon will have to equal the pressure outside the balloon. Otherwise, the volume just changes. So here's, these are supposed to look the same. So here's at a lower pressure. Okay. And then what happens if I increase the pressure? If I increase the pressure and the force stays the same, the force has to be equal in and out. What happens to change it? Well, the area decreases. So if I increase the pressure here, the pressure inside still has to be the same. But in order to do that, the volume of the balloon decreased. So if I took a 1 liter balloon at sea level and I took it down to 33 feet in the ocean, that represents another atmosphere of pressure. 1 atmosphere is equivalent to 33 feet of seawater. So if it's 1 liter at 1 atmosphere, if I put it at 2 liters, the volume's only half. Make sense? When I used to do a lot of diving back in the 70s, which is one way how I got myself through college, I had the GI Bill, I had diving, and I made a lot of money off of diving. I would have people sit on the boat, sit on the shore with a dive tank, and just breathe. If you could make that dive tank last for 60 minutes on shore, if you went down 33 feet where you have twice the atmosphere, when you open that up to ambient pressure, it's only half the volume. You got 30 minutes to stay underwater, and you run out of air. If you go down another 33 feet down to 66 feet, that's 3 atmospheres pressure. You get only 1/3 the volume. You got only 20 minutes to stay down there. Then we have pressure with a fixed volume. So here, the pressure in does not have to equal the pressure out. So that's either a bomb that explodes or, say, a bomb that implodes if the container walls break. So how does a firecracker work, or a bullet, or things like that? Firecracker, you take paper, you roll gunpowder up in it, and that paper acts like the rigid container. And when the gunpowder burns, it goes into the gaseous state, produces heat to expand that gas. It basically breaks the container. Popcorn works the same way. Okay. So any questions so far? So V represents volume. If we have a volume change, we might say V1 versus V2. N is the number of moles. It's the sum of all the gas particles. So if you had a tank with half a mole of oxygen and half a mole of hydrogen, then N would be 1 mole. And R represents the universal gas constant. So in other words, if I were to solve PV equals nRT for R, then I measure all these variables right here. Notice the units would be pressure, volume, moles, and Kelvin is temperature, right? We get this number and it's a constant. Doesn't matter if it's a pure gas, a mixture of gases, whatever, it's always a constant. And so that means if this is a constant, what if I say set of conditions 1, I do the math, I get this constant. Then set of conditions 2, I do the math, I get that same constant. If this is equal to R and this is equal to R, therefore this is equal to this. And here is another form of the ideal gas law. It does not contain R in it. So if I added more gas to a container, N1 then turns into N2. And all these other things will change. And T represents temperature. And so the gas laws were really the reason why they had to come up with a new temperature scale that was never below 0. So look what happens. I solve for volume, for example, right? Say we're looking at air at 1 degrees. You got 1 degrees Celsius in here. That's a number, that's a number. They're all positive numbers, right? So you get a value for the volume. Then you drop the temperature down to 0, and all of a sudden the volume becomes 0? Doesn't make any sense. Say you drop it down to -1. Then you have a negative volume? What the heck is that? So they needed a temperature that was always going to be positive. So notice what I did here. Here is the temperature in Kelvin, and then here is in Celsius or centigrade. And I plotted a gas, temperature of a gas versus, say, the pressure. So I can get data up here. Here's the temperature, I can measure the pressure of the gas. I move down here, I can measure the pressure of the gas. I move down here, I can't measure the pressure of a gas because it's not a gas anymore. Turned into a liquid. But if I take this data and I extrapolate it out to wherever it goes, you know where it goes? No matter what the gas is, another gas might do this, another one might be doing that. They go to the same place every time, negative 273.15. If I plot the volume of a gas, I get the same number. If I plot the kinetic energy or the state of randomness, I get the same thing. So that is a magic number. And they decided, we'll call that 0 degrees Kelvin. And theoretically, that's the lowest possible temperature in the universe. So entropy is a state of randomness. So what is zero entropy? It's a perfectly ordered crystal at 0 degrees Kelvin. Perfect order. What would you have to do to turn that crystal at 0 degrees Kelvin into a gas. You would have to heat it up dramatically, and all the particles are moving all around. So hot gas is maximum randomness, maximum entropy. Okay. So here's the part that people hate. Doing gas problems. You know what? I hate doing gas problems because they're really not that important. So a lot of textbooks, okay, most all of them, okay, what they do is they take you through a bunch of things that were discovered with the equations that go with them, along with the names of the people who figured them out. There's Boyle and Charles and Gay-Lussac and Avogadro. Anyway, I don't care about those famous dead guys. And I don't want you to have to memorize a bunch of equations. I don't want you to memorize anything. I want you to understand things. So I'm going to show you a way that you won't have to memorize all those things. So, 5 different kinds of gas problems. One is a missing variable. You're simply going to use PV equals nRT. That means if I'm going to ask you for P, I have to give you all those other things, and you simply solve for it. Another type is a change in conditions. Say you're reading a problem, oh, the gas was heated from so-and-so to so-and-so. That means that there's a T1 and a T2. So you use this for a change in conditions. And then there's another type where you have to use this conversion factor right here. 1 mole of any gas at STP will occupy 22.4 liters. This is not very important because I can also get the same information using PV equals nRT. That's where this came from. Then another one is that we might solve for the density of a gas at STP. Very simple, actually. So the molar volume of any gas at STP is 22.414 liters. That's what we have over here. Okay? But the masses will be different. So for oxygen at STP, 1 mole will always be 32 grams, but at STP, its volume will be 22.4 liters. So what is the density of oxygen? I just do the math. 1.4 grams per liter. And then there's another one called partial pressures. And here I did put the name just because I know it's important in biology texts that you know that Dalton's law of partial pressures is simply the law of partial pressures. But because they use it in biology texts so often, I thought we should put the name there. So here's what it means. The total pressure in a container is equal to the sum of all the partial pressures of every single gas. So if I have a container, I got 1 atmosphere of nitrogen in one container, another atmosphere of helium in another container. When I add those two together in the same container, pressure simply doubles. It's additive. And then there's math that can be involved. If I know this, and I know this, I could calculate this. That's all. And there's other types of gas problems. So I thought I would throw this in. Just, I don't know why I did this. So what is flatulence and acidification? Here is starch. amylase is supposed to break it down into glucose, which can be absorbed. Partially digested stuff cannot be absorbed by your intestines. So what happens to it? It keeps going down your intestines until it gets to where the bacteria are. And they're like, oh, thank you so much for supplying all these incomplete digested glucose products. Because we're going to digest them, even though you didn't. And what do they do with it? They do the same thing you would do with it. They produce CO2 and water. That combines into carbonic acid, which then gives you an acidified pH. Your intestines are supposed to be pH neutral. But if you don't completely digest your food, then you may have acidification and gasification due to bacterial metabolism. Okay, well, let's look at a few gas problems. Balloon has a volume of 2 liters. Oh, V1, or V, I should say, at 25 degrees. Oh, there's T, but I have to convert it to Kelvin. 1 atmosphere, oh, that's P. How much gas is there? I'm just solving for N. So I take P equals nRT, solve for N, plug in all my numbers, and I get the answer. So what's important here is that you do the algebra correctly and that you make sure all your units are compatible and they actually will cancel out. If I use torr over here and atmospheres over here, it's not going to work. If I use milliliters here and liters here, it's not going to work. And you always have to use Kelvin. What is the volume of so many moles of gas given the temperature and the pressure? Again, it's a missing variable problem. We're just solving for V. And then this third example here is not a gas problem. I'm just trying to show you some easy manipulations of the most complex equation that we have here. So what if we had to solve for N2? Oh my God, that's in exactly the wrong place, isn't it? But if this is equal to this, I can just flip these around. That's exactly what I did over here. Now I can just ignore this. Now I have N on the correct side. And then I can take this right here and simply flip it upside down. Now I have N exactly where I want it, N2. So to isolate N2, I have to get rid of T2, I have to get rid of P2, I have to get rid of V2. And then whatever I do over on this side, I have to do the same thing over on this side. So when I multiply this out, this is what I get. This is a couple of quick, easy maneuvers that makes you get to the answer quickly. So look at this one. A gas at 2 atmospheres, 25 liters, 300 Kelvin is heated. What does that mean? There's going to be a T1 and a T2. I got to use this equation. So I solved this problem by going through and trying to find all the different variables. So 2 atmospheres must be P1. P2 is where? Oh, that's the new one I'm trying to find. And V1 is 25. Where's V2? Oh, at constant volume. That means that V1 is equal to V2. So this must be T1 is heated up to T2, right? And then I'm looking all through this problem. Where do they mention N? N is the number of moles. Well, there was no mention of N. So the only solution is that N1 is equal to N2. And you know why that's important? Because that's the reason why you can do it my way. You have to recognize that right there. So the ones in blue right here simply cancel out on both sides of the equation. So that leaves us the simplified equation, which is really, that's Charles' law. But here's what textbooks would want you to do. Read this and then decide, oh, that's Charles' law, and then come up with this. It's ridiculous. You don't have to do that. So then it's this matter of algebraically solving and then substituting numbers. So here's another similar one. Then look at this one. What is the volume of 1 mole of nitrogen gas at STP? It's a missing variable problem, right? They want you to solve for the volume. They're giving you N is 1 mole. Standard temperature is 0 degrees Celsius and 1 atmosphere pressure. So all I'm doing is putting in those values, and what do I get? 22.4 liters. 1 mole at STP is giving me 22.4 liters. That's the conversion factor that most textbooks want you to memorize. What is the volume of 2 moles at STP? Look, 2 moles gives you twice that amount. When all of these other things are constants, then the relationship between moles and volume is a direct proportion. When you're asked questions like this, how many moles of nitrogen and 25 liters at STP, if you have that memorized, then you can just do this. If you don't have it memorized, then you can just plug it into PV equals nRT. So why do we even have that? Where to go? Why do we even have this? Well, here's one reason. So if you look at this problem, a balloon has a volume and whatever, blah, 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 blah. What is its volume? So I go and I calculate its volume, but now it's at STP. I calculated using this relationship what the volume would be at STP. And then I can use this conversion factor to simply turn that into moles. That's why it's valuable. So here's another problem over here. And what I want to do is show you something. See how I solved this problem right here? First I solved it using, where are we? 25 degrees. Then I solved it again using 800 degrees, and I got 2 different numbers, right? Look at the next problem. I did really the same thing, but instead of solving for it twice, I simply used this, and I got the same answer. Now, is this magic? No. Why does it work? Because there's only one ideal gas law, PV equals nRT. And this came from PV equals nRT. It's just another form of the same equation. So here is a calculation for the density at STP. So for nitrogen, 1 mole of N2 is about 28 grams. That's the gram molecular weight, the molar mass. And at STP, it's going to be 22.4 liters. So the density is simply mass over volume. And that is the approximate density of air, because nitrogen is about 79% of the air. Oxygen's about most of the rest, and oxygen has a similar molar mass. So I remember when I first saw Costco using nitrogen instead of air in its tires, I'm like, oh, what's this, some kind of a scam? But then I thought, they must be doing it for a reason. And so my wife has expensive tires. They're filled with air. And I'm constantly putting air back in them, I don't know, once every 3 weeks maybe. I have tires from Costco with nitrogen in it. I've never had to put more nitrogen in them. So oxygen escapes 3 or 4 times faster than nitrogen. And I thought this was ridiculous because this is what I knew. The molar mass of oxygen was bigger than that of nitrogen, so it doesn't make any sense. So I looked up the radius, and actually the radius is actually bigger. Okay? So that's the reason why. There's 2 ways to calculate the radius. Okay? The other thing is that oxygen is corrosive, nitrogen is not. Air contains moisture. Costco's nitrogen is dry. So what is the density of hydrogen at STP? Okay, look at it. It's really light. So the early dirigibles used hydrogen because helium was really just too hard to get. So anyway, you may have heard about the Hindenburg disaster. It was on the cover of the Led Zeppelin album. And if you look at what's going on right here, people might say, oh, it's blowing up. But it is not blowing up. It is simply burning from the outside. It did not blow up. Why would they think that they could fill this up with hydrogen and think that they're safe? Because in order to burn the hydrogen, you have to have oxygen. So if you were to go in here with a match, first of all, you're not going to survive in there because there's no air, you'd die. But if you lit the match, it wouldn't do anything because there's no oxygen in there. So you can see it's burning from the outside, which is the same thing that the Bunsen burner does. So the butane, propane, whatever it is, comes through here. There's an air hole here, so as the gas goes through here, it sucks air in here, and you get some mixing of oxygen in here, but it's usually not enough to make it burn well. It has to get out here and use oxygen from the air. So when I'm teaching labs, I routinely, in the beginning say, take this piece of wire and stick it through here, and you tell me where it's hot and where it's not. And you can see that the hottest place is about right here, somewhere up in here. And right, that first cone right there is really not even hot. This is barely burning, if at all. So the flame actually lives on that surface of the gas coming out of the tube. Do I have to be worried about when I turn this off, the flame's going to shoot back down in here and blow the building up? No, because there's no oxygen there. So the atmosphere on planet Zoom is made up of this. So if the total pressure on the planet is 2 atmospheres, what is the partial pressure of each gas? Well, here's what Dalton's law says. The atmospheric pressure is the total pressure. It's a combination of the pressures coming from all the gases. So the total pressure is 2 atmospheres. It's 25% oxygen. So 0.25 times that means that the partial pressure of oxygen is 0.5 atmospheres. Similar for methane is 1 atmosphere, and chlorine, and you see that adds up to be the 2 atmospheres. So what would happen if you took all the oxygen out? I removed all this. I'd remove this. Then the total pressure would be coming simply from methane and chlorine, and it would be 1.5 atmospheres. If I took out all the gases, the pressure would be 0. And what would be the partial pressure of each gas if the atmospheric pressure was doubled? Okay, so for example, if you took the volume and you decreased it by 2, the pressure would about double. So then mathematically, this is true. So if I take that equation, multiply everything by 2, it should add to be 4 atmospheres. And here you see that it did do that, right? Composition of the atmosphere didn't change, but the partial pressures did, and thus total pressure. So that's probably a good place to stop. So does anybody have any questions on chapter 15 so far?
I actually had a question about the homework. For homework 13, I was wondering, for ammonium carbonate, even though it doesn't have like a metal in the composition, would it still be an ionic molecule because they're both ions?
Exactly. Yep.
So it doesn't necessarily have to have a metal in it. It just has to have charges.
Exactly. Full charges.
Okay.
Exactly.
Thank you.
Mm-hmm. And the ammonium ion is the only common polyatomic cation, positively charged ion. Yeah, there's not very many of them. Yeah. Okay, so any other questions? So for the biochem students, you have exam 3 on Monday and Tuesday. And for the Chem 100 students, you have exam 2 on Monday and Tuesday. And okay, what time was I going to do that? I think it's 1:30 I was going to do the, which is now, the review for Unit 2. So any of you are welcome to stay for that. I think what I'm going to do is I'm going to stop recording. Where did that go? So I'm just going to end it and then sign on again, okay? So we have separate videos. So if you're going to come for the review, I'll be right back.